Thank you, Angela, and hi, everyone. Thank you for coming to my presentation today. I love talking about this. I actually have been doing this presentation at multiple different places since 2022. So let's get started. All right, so a little bit of background. I did my first risk assessment at a rare earth element mine in 2021. And I found that whenever I did this assessment, I was left feeling like I wasn't able to assess the hazards as best I could. And there was a few gaps in the legislation and the guidance. And because of that, I decided to do these presentations. And so since I've been involved in a few more projects, particularly during the early phases of these projects before mine development, which is the best time to assess risk and plan for controls. And I won't be showing you any confidential information for my projects, any results, because they have been confidential, and most of the data is from literature reviews, but I'm going to share with you some of the lessons learned from the assessments that I've done. So this is the agenda today. We're going to go over what rare earth elements are and what the industry looks like globally, because before I did a risk assessment at a rare earth element mine, I didn't really know what they were. We're going to talk about the two unique hazards associated with this industry. Then we'll talk about the legislation and guidance that's associated with them. And then I'm going to go over some guidelines on how to do a baseline exposure assessment. So what are rare earth elements? This is the first poll. So you can tell me how much you know about them, just to gauge with the audience, what knowledge the audience has. Right. It looks like we have a pretty good spread for the first three. Either people know nothing, heard about them in the news, or have done some reading about them. So it's maybe good there's no experts on the topic, or else you might find this a little bit boring. All right. I'm going to share the results now. Can everyone see that? What the results are?
Yes.
Great, great, awesome. Okay, so yeah, nice spread between nothing and you've done some reading about them. Great, good to know. All right, so what are rare earth elements? For the people who know nothing, they are these 17 elements on the periodic table. There are 5 lanthanides, so the ones down at the bottom there. And then also scandium and yttrium are lumped in because they're found in the same ore bodies and they exhibit similar chemical and physical properties. This is a breakdown of what they're used for. This is what they were used for in 2021. So you can see that the single largest end use for rare earth elements are magnets, and that's because neodymium, which is a rare earth element, together with iron and boron, are the strongest magnets known, and they're used in a variety of different technologies, including the magnets in your microphone and speaker in your smartphones. They're also used for windmills and electric vehicle electric vehicles. And so they are quite important for the green energy transition and technology. And so those are the ones that you see the most often. And so these are quite important. And as you might have guessed, these are pretty important for meeting the Paris Agreement goals. And so this figure is taken out of the International Energy Agency report in 2022. And these are what are called critical minerals. You probably heard that term as well in the news. And those are the minerals that are the most important and require the most increase in production to meet the Paris Agreement goals and aid in the clean energy transition. And so this shows how much more of these critical minerals that we need to have compared in 2040 compared to their 2020 levels. So we need 7 times the amount of rare earths by 2040 to meet the goals. And so that's a lot of mining. And so that's part of the reason why this is an emerging and expanding industry. This is a quick look at the global mine production of rare earths by country. And this is starting in 1985 all the way up to 2022. And you can see that China dominates the market. And this is for mining in refinement of rare earths. It's even more of a monopoly that China has. Around 90% are refined in China. And so this is another part of the reason why we're seeing more and more rare earth element mining projects in North America, because we want to have a secure supply chain of rare earths. And you've probably seen headlines, something like this: the US partners with Canada and other countries to secure a supply chain of critical minerals, and that includes rare earths. And so right now there's over 50 rare earth element mining projects in Canada and a lot in the States as well. So next we're going to take a look at the risk to worker health, and we're going to be focusing on the 2 unique hazards. So these are some of the hazards that you would assess in a baseline risk assessment. The red ones are the ones that are unique. So firstly, rare earth element particulate is unique to rare earth element mining. You are going to be breathing in rare earth element particulate whenever you're mining for it and concentrating the rare earth elements. And secondly is naturally occurring radioactive materials, or NORMs. And that's because thorium and uranium co-occur in rare earth element mineral deposits. And this is unique not because there's no ionizing radiation in other industries in Canada, but because of the way that they're regulated in Canada, and we'll go over that. And also because this industry has more thorium than other types of mines in Canada. And so that needs to be taken into consideration whenever you're doing risk assessments, and that's quite unique. And then there are other occupational health hazards in mining. These are some of them up here. And so those ones can't be missed as well whenever you do a baseline risk assessment. So we're going to look in a little bit more depth at the 2 unique hazards. So we'll start with rare earth elements. So the main takeaway here is that the research is quite limited on the health effects of rare earth elements. And most of the data comes from laboratory tests in animals and human cell lines. There are some human studies. Most of them are case reports of disease and geographical studies of people living near rare earth element mining regions in China. And I got all of my information from 4 literature reviews. The most recent one is from 2021. And it actually stated in that there's no known epidemiological studies for occupational exposure for rare earth elements. So that creates a knowledge gap with respect to the possible long-term health effects of being exposed to rare earth elements. But from the information that we do have from the human data, there is some evidence that the exposures affect these different systems in the human body. So the ones that you see over on the right, the respiratory, blood, neurological, kidney, and liver, with the one being the respiratory being the most important in an occupational setting. So we know that all the rare earth elements, all of those 17 elements, have similar physical and chemical properties. Whenever you look at the animal lethality data, the LD50, it's quite similar. And so the range is up here for mice and rats. And as I said, the respiratory effects are the ones that are the most important in an occupational setting. And we know that they're poorly absorbed in the lungs. Short-term exposure is associated with acute irritative bronchitis, and long-term exposure is associated with pneumoconiosis and progressive pulmonary fibrosis. All right, so on to the naturally occurring radioactive materials. So we know that ionizing radiation can cause cancer. And so there's been, lots of research done on this. So the radioactive decay of uranium-238 and thorium-232 in the rare earth element ores can cause low-level chronic exposures to ionizing radiation. These are the exposure pathways that we want to be focusing on whenever we're doing a risk assessment. And so the exposure pathways for ionizing radiation exposure from norms are firstly direct external gamma radiation. And the second one is the inhalation of radioactive gas and the radioactive progeny. And the radioactive gas that comes from the uranium decay chain is called radon, or radon-222. And probably everyone here is familiar with that one, but you might not be as familiar with the one that comes from the thorium decay chain. It's called thoron, or radon-220. And so that one actually requires a different method of sampling. And so that one is sometimes missed in some of these risk assessments because there is a lack of a guidance on how to measure thoron and its radioactive progeny. The third one is the inhalation of airborne long-lived half-life radioactive dust. And then the last one is ingestion of radioactive materials. And this one is less important than the first three, just because you don't normally ingest a lot of radioactive materials, and they're not particularly digestible. And so that one, it's important to have good housekeeping at your rare earth element mine, but that one isn't factored into the total dose. Just the first three there. So I wanted to give you an idea of what sort of concentrations of uranium and thorium you might see at a rare earth element mine. So in this table, the first three locations are rare earth element mines around the world, some of the most significant ones. So the first one is Bayan-Obo in Mongolia, and Mountain Pass in the United States, Mount Weld in Australia, and then I also put some Canadian deposits up there. And so there's two takeaways to bring from this slide. The first one is that the uranium concentrations are actually quite low, especially whenever you compare them to the uranium mines in Canada. So a low grade ore body for a uranium mine is around 1,000 ppm of uranium oxide, and here we only have around a maximum 90. Still significant though, in the sense that you need to be doing a risk assessment to see what the ionizing radiation exposures are from the uranium. And the second takeaway is that the thorium is in a much higher concentration than the uranium. And so it's important to take into consideration the ionizing radiation from the thorium decay chain as well. All right, so on to the legislation and guidance for the two unique hazards. We're going to start with the rare earth elements, and brings us to our next poll. how many of the rare earth elements have occupational exposure limits? And by occupational exposure limit, I mean like one that's written into legislation or published by ACGIH. All right, so you can see that people think there's either none or there's one for all of them together, the most. Quite a range though. All right, let's see. So the people who said that there's one were the one that was right. There's one occupational exposure limit out of 17, and it's for yttrium. And it was published quite a long time ago by ACGH, last updated in 2001. And US OSHA and Canadian legislation has adopted it. And it's an 8-hour time-weighted average of 1 milligram per meter cubed. And it's to protect against pulmonary fibrosis. It was created based on one study of an animal study of a large dose in rats. It commented that toxicity data in industrial reports are limited, which we went over earlier. And there was insufficient data to recommend whether or not skin was a major route of exposure, whether it's a sensitizing agent or whether or not it is a carcinogen or not. So if you only have one occupational exposure limit, but 17 elements to deal with, then what do you do? And I wanted to bring up that it might be tempting to use the nuisance dust limit or the particulates not otherwise specified or PNOS limit. ACGIH and different jurisdictions have adopted guidance values for respirable and inhalable dust. But this is to limit the amount of dust burden in the lungs, and it's for non-soluble, relatively non-toxic dust. And from the lethality data in rats and mice, we know that rare earth elements are moderately toxic, and so this is not appropriate to assess risk. And so I was able to find one health hazard evaluation that was done on rare earth elements in particular, and it was a NIOSH one done in 1989. And this was for worker exposures to metal powders at a manufacturer of magnetic products. And they used 2 rare earth element powders, one for neodymium and one for dysprosium. Those are 2 rare earth elements. And they made the assumption that these 2 rare earth elements have similar chemical and toxicological properties to yttrium. And because of that, they use the yttrium's ACGIH TLV of 1 milligram per meter cubed, 8-hour TWA. And so whenever we went to the rare earth element mine to do an assessment, we made a similar assumptions. We came up with what I'm calling the WSP-derived guidance criteria. It's non-published, but it's a value that could be used if you're looking for something to use. And we decided to lump all the total rare earth elements together instead of comparing them individually. And this is because in mining, you're exposed to all of them together and not in isolation as they would have been at the the magnet manufacturing facility. And so these are the assumptions that we made. Okay, on to the legislation and guidance for the norms. So not like the rare earth elements, the ionizing radiation actually does have well-established dose limits or occupational exposure limits. And the International Atomic Energy Agency, or the IAEA, has the most current definitive reference for dose limits, and a lot of different jurisdictions, including Canada, base their radiation protection limits on this. So the one that you are probably most familiar with is an effective whole body dose of 20 millisieverts per year. And I should mention that it also includes the as low as reasonably achievable, or ALARA principle. And because it's a carcinogen, then all radiation doses should be maintained at as low as reasonably achievable. So why is it a unique hazard in Canada? And the same goes for the United States as well. It's because our robust legislation for ionizing radiation is found in from the CNSC, or the Canadian Nuclear Safety Commission. But this only applies to rare earth element mines if uranium and thorium are sold as byproducts and commercial byproducts, because then they would be part of the nuclear fuel cycle. And so, for example, uranium mines and nuclear power plants fall under the CNSC, but rare earth element mines do not. And the other thing to note is that Canadian uranium mines don't have a substantial quantity of thorium in them. And so the legislation and guidance that Canada has provided primarily addresses the uranium decay chain and not the thorium decay chain. And so because of that, you might miss an assessment of thoron and its radioactive progeny. And so rare earth element mines are regulated provincially and territorially, and a lot of the times the worker radiation dose limits can be out of date, and they are normally there to address radon and underground mines, and they might not address the other forms of exposure adequately. Okay, so if you're looking for a way to address thoron and its radioactive progeny, there are some good sources from Australia, because they do have rare earth element mines in production already, but they also have more thorium in their uranium deposits. And so I just put this up there so you'll know where to go if you need to sample for thoron and its progeny. Another resource that will be coming out soon for an assessment strategy is the ANSI and 13.8. It used to be called Radiation Protection in Uranium Mines, but they're revising the title to Radiation Protection in Mining. I sit on the committee for this, and I'm not sure exactly when it's going to be out, but it'll be a good resource to look at for an assessment strategy, because they are changing it because they recognize that the legislation in the United States doesn't adequately address the ionizing radiation hazards from some other mines, but in particular rare earth element mines, because the deposits co-occur with uranium and thorium. All right, and then the assessment strategy that I used whenever I did the assessment was the Health Canada guidelines for the management of norms. And this is a more detailed guidance than the mining regulations. And it's a set of graduated levels with increasingly stringent radiation protection measures based on the calculated annual dose for the workers. So for example, if the calculated annual dose is less than 0.3 millisieverts per year, then it would be classified as unrestricted, and there's nothing required other than public access being restricted. And then it goes up from there, where if you have a higher calculated annual dose, you need more assessment and control measures. And so this is a really good resource to go to when the mining regulations are not up to date for rare earth element mines. So I wanted to give you an idea of what sort of doses there might be at rare earth element mines. And so these are work your annual effective dose estimates in millisieverts per year at 3 rare earth element mines, one in Mongolia, the United States, and Australia. And they're broken into the different exposure pathways that we talked about earlier. And so there's 2 takeaways from this table again. The first one is that the total dose ranges from 1 to 4, which is not extremely high. The exposure limit is 20 per year, but it is significant enough that you need to be putting in different control measures and doing an assessment. And the second takeaway is that thoron and their progeny can take up quite significant piece of overall exposure. So especially for the mine in Mongolia here, you see that it actually contributes the most out of all the different exposure pathways. And so if you are leaving that one out, if you didn't know to sample for thoron and its progeny, you would be underestimating the risk for ionizing radiation from rare earth element mines. And I should say that these are taken from the highest risk workers at these mines. So not everyone has a total annual dose of 1 to 4 millisieverts per year. Okay, and that brings us to our last poll. Why might exposure to ionizing radiation be underestimated as part of an exposure assessment in rare earth element mining in North America? And just pick the best answer here. All right, they should be up there. I should be able to see them. And so the one that is the most correct is B. And so most people got that one because there's a lack of guidance on how to measure thoron and its radioactive progeny, although all of them have an element of truth in them. So there is an occupational dose limits for ionizing radiation, but they can be out of date and they mostly address radon exposure. And most of the rare earth elements are mines are open pit, actually, which might mean that you might not do the assessment or miss some of the exposure pathways if you don't think they're significant, like external gamma. And there might be a lack of trained professionals. It's quite possible. So good job on that one. Okay, so now we're going to go over some recommendations for baseline exposure assessment. So for rare earth elements, you should be collecting personal samples for inhalable and respirable rare earth elements. I put in personal just because then you can compare them to the guidance value, which I showed you. And I also put in respirable rare earth elements in there just because, you know, if you have the budget and the time for it, it would be good to collect both fraction sizes, because in the future there might be respirable occupational exposure limits for rare earth elements, since there's not a lot of research done on them so far, so you could do a retroactive exposure assessment that way. And the second step is to quantify the rare earth elements, which is preferred, or estimate the concentration based on previous ore assays. And so there's no NIOSH method for rare earth elements yet, but you can use the same method as a lot of the other metals out there, and you can quantify them. So if you have the budget for that, it's definitely the best way to go. You can estimate the concentration based on the previous ore assays, but that's going to be an overestimate or underestimate, depending on what part of the mining cycle you're in. So for example, if you're, in the open pit, and you might be overestimating the exposure, but if you are refining the rare earth elements, then it's probably an underestimate. So you can quantify them. That's the best thing to do. And then the third step is comparing the full shift inhalable total rare earth element concentration to the guidance value of 1 milligram per meter cubed, or if you can come up with a better guidance value, you could use that too. And then the fourth step is to implement control measures and devise future sampling plans based on these results. Okay, on to ionizing radiation. So the first step, you're going to collect your measurements. You're going to do measurements for external gamma. You're going to do separate measurements for radon progeny and thoron progeny. And then you're going to do some measurements for long-lived radioactive dust. You are going to estimate worker dose from the sum of all these exposure pathways and compare them to the dose categories in the Health Canada norm guidelines. So that's what I recommend doing for now. And then you're going to implement control measures and implement future sampling plans based on the results of the assessment. Okay, and just one more slide, some future considerations on how to close the gaps that we discussed today and prevent disease. So for the rare earth elements, we know that there's a lack of research and a lack of occupational exposure limits, so we do need more of this, but we should be assessing risk based on the information that we have, so we can quantify the rare earth elements. So you can take air samples and you can do your best at assessing the risk with that. For ionizing radiation, from norms, we need to address both the uranium and thorium decay chains when assessing risk to norms. So that means taking thoron progeny samples as well as radon progeny samples. And there is a lack of regulatory limits and guidance for norms in the rare earth element mining industry. And so what you need to do is you need to adopt a strategy for assessment and control. And lucky enough, Canada has good guidance for ionizing radiation. We've had uranium mining for a long time, and so we can use the same controls and assessment strategies for rare earth element mining. Okay, and these are my references, and that is it. Thank you.